Random variables will remain with us until the end of this course, and so it is better to underline what we have just seen. Given a sample space S, a random variable x is simply a function from S to the set of real numbers. If we apply x to the whole sample space, then we obtain the so-called range of the random variable. If this range is a finite subset of R, then we say that x is a discrete random variable. Otherwise, we say that it is a continuous random variable. Notice that the name random variable can be misleading. In fact, as a function, x is deterministic. What is random is the choice of the events E in the sample space S. We have seen that random variables become interesting when we mix them with probability functions. First of all, we have seen that we use this symbol here in order to denote the probability of the set of events that are mapped to the interval AB by the application of the random variable x. If the set AB is inferiorly unbounded, which means that A is equal to minus infinity, then we write this symbol simply as P of x less than B. Thanks to this symbol, we could define the important concept of cumulative distribution function of the random variable x, which is nothing but the function fx defined over the reals and that takes values in 0, 1, and it's defined like this. Take any real number x, then the cumulative distribution function related to the random variable capital X applied to small x is simply the probability that the random variable is less than or equal to x. We call the cumulative distribution function of the random variable x the CDF of x for short. The CDF of a random variable allows us to give an alternative description of its quality as being discrete or continuous. In fact, we have seen that x is discrete if and only if f is a step function, and then x is continuous if and only if f of x is a continuous function. The concepts related to densities are really important, and so it is better to underline them in a short video. First of all, we note that given a random variable x, even if its cumulative distribution function and its density are written with very similar symbols, they are two different things. In fact, the cumulative distribution function is written with a capital F, and it's a function from R to 0, 1, while the density is written with small f, and it's a function from R to 0 plus infinity. We have seen that the definition of density changes accordingly to the fact that the random variable x is discrete or continuous. In the first case, the definition of the density is pointwise like this. In the second case, the density appears in this integral formula. In the case in which the random variable is continuous and its cumulative distribution function is differentiable, we have a very important relation between these two objects. In particular, we have that the density is the first derivative of the cumulative distribution function, or equivalently, the cumulative distribution function is given by the integral of the density. Then we have also seen that we use this symbol here to denote the fact that x is distributed as its density. In the previous videos, I recalled the most important concepts about random variables, probability distributions, and densities. In this lesson, we're going to introduce other relevant features of random variables that go under the general name of moments. We start, of course, with the easiest moment, that is the expectation value, or mean, which is nothing but the weighted average of a random variable with weights provided by its density. As always, this concept will be easier to understand if we start with a concrete example. In this case, we take this set of 20 outcomes of rolling a die. If we sum all the outcomes and divide by 20, we obtain 3.35. A value like this was to be expected, right? In fact, since all the numbers from 1 to 6 have the same probability of occurrence, we expect the mean value to be close to 3. Now, mathematically speaking, there is another way to compute the average. In fact, we can observe that 1, 2, and 6 appear 4 times, 3 and 4 appear 3 times, and 5 appears 2 times. For this reason, we can write the average A as follows. We multiply 1, 2, and 6 by 4. Then we multiply 3 and 4 by 3. There it is. And then we multiply 5 by 2, and we sum together all these numbers. Of course, we have to divide by 20, and then we recognize that we can factor out 4, 3, and 2 as written in this formula here. Now notice that these three factors are all divided by the denominator 20. And so we can rearrange the formula for A like this. Of course, 4 divided by 20 can be written as 1 divided by 5, and 2 divided by 20 can be rewritten as 1 divided by 10. You can check that what we obtain using this strategy is again 3.35. These fractions are usually indicated with the symbols W1, W2, and W3, and they are called the weights of the weighted sum. Notice two key properties. All the weights are numbers between 0 and 1, and counted with the number of times that they repeat, they sum up to 1. Why that? Well, W1, that is 1 over 5, repeats 3 times. In fact, recall that it is the coefficient associated to 1, 2, and 6. W2, that is 3 over 20, repeats 2 times because it is associated to 3 and 4. And W3, that is 1 divided by 10, appears only once because it is associated just to the number 5. If you perform the corresponding computation, you get exactly 1. Now recall that we have already encountered two objects that behave exactly like this. The probability mass function of a discrete random variable has exactly the same properties, and also the probability density function of a continuous random variable if we replace the discrete sum with an integral. So, to resume, if we multiply the values that a discrete random variable can take by the corresponding probability mass function and then we sum, we get the mean value of the random variable, but written as a weighted average with weights given by the probability mass function. And the same can be said for a continuous random variable when we replace the probability mass function with the probability density function and the sum with the integral. Let's see how people working in probability define all this. For a discrete random variable x, its expectation value or mean is written like this. So you see that there is an e that is reminiscent of expectation, and then there is the random variable x written within square brackets. The expectation value is the sum over the possible values that the random variable can take, multiplied by the probability mass function of these values. For a continuous random variable x, the symbol remains the same, but the definition changes because we have to use an integral and the probability density function. And of course, this definition makes sense if and only if the integral gives a finite value. In the following theorem, we report the most important properties of the expectation value. Consider two real numbers a and b and two random variables, discrete or continuous, x and y. Then, the first properties simply say that the expectation value behaves linearly with respect to random variables. This is the property that resumes this behavior. If you compute the expectation value of a times x plus b times y, you have a times the expectation of x plus b times the expectation of y. A few words must be said for this property here, starting from the meaning of a used as a random variable. What we mean when we use a real value to denote a random variable is the random variable that always takes this value, that is, the constant random variable x that associates to every outcome of the sample space the real number a. It is then clear that the only expectation value of the constant random variable a is a itself. The other very important property of the expectation value is the fact that we have this factorization here, that is, the expectation of x times y is equal to the expectation of x times the expectation of y, if and only if x and y are independent random variables, where of course we must define what we mean with independent random variables. In order to do that, mathematically speaking, we should introduce the so-called joint probability distribution and marginal distribution. However, this will take us too far, and I prefer to give you just the practical meaning of independence, which is the following. Knowing the value that x takes in S gives no information about the value that y can take in the same outcome S. We will examine nice examples of expectation values after the introduction of the concept of moment of a random variable. Consider a positive integer number n, then the nth moment of a random variable x is the expectation value of the nth power of x. We indicate this number as mu tilde of x. Of course, when n is equal to 1, this becomes x, which means that the first moment of x is simply its expectation value. The reason why we introduce the symbol tilde is that in practice we never work with moments but with centered moments. The nth centered moment of the random variable x is the expectation value of x minus its expectation to the power n. As we have said before, we must interpret this notation as x minus the constant random variable that takes always the value e of x. As a nice exercise, you can understand the name centered by answering this question. What's the first centered moment of any random variable x? Try and think about it. The most important moment of a random variable is the one of order 2, which bears a special name. The second central moment of a random variable x is called its variance, and the positive square root of the variance is called standard deviation, written with the symbol sigma of x. The meaning of the variance is the following. The variance of x gives a measure of the degree of spread of the random variable x around its expectation value. So large values of the variance mean that x varies a lot. On the other side, if the variance is 0, then it means that x is equal to its expectation value with probability 1. That is, there is no variation in x at all. The qualitative interpretation of the standard deviation is exactly the same as that of the variance. The only difference between the two is that the unit of measurement of the standard deviation is exactly the same as the one of the random variable x, while that of the variance is the square. It is useful to have an alternative formula for the variance given by this equation here. That is, the variance of x is given by the expectation of x squared minus the square of the expectation of x. We can easily prove the equivalence between the two definitions by developing the square here. As you know, the square of a difference is the square of the first plus the square of the second minus 2 times the first times the second. Using the linearity of the expectation value, we can rewrite this expansion like this. And finally, we notice that both this quantity and this quantity are constants. We know that the expectation value of a constant is the constant itself. And in this case, we know that we can take off the constant and put it in front of the expectation value. Therefore, the variance can be written like this. But notice that this is nothing but the square of the expectation value of x. Hence, we can rewrite this simply as minus the expectation value of x squared. And this allows us to prove the equivalence between the two formulas. We can easily understand why it is useful to have two formulas to compute the same value by considering the case of a continuous random variable. Depending on the analytical expression of the density, sometimes it will be easier to compute this integral, and sometimes it will be easier to compute this one. Since the definition of variance involves the square of a random variable, it is very unlikely that the variance preserves the linear behavior expressed by the expectation value. In fact, the following theorem establishes that the variance of a times x plus b, where a and b are constant, is given by a squared times the variance of x. That is different than a times the variance of x plus the variance of b, which is the formula that we would have obtained if the variance had a linear behavior. To prove this formula, we simply use the definition of variance. So we write variance of ax plus b is the expectation of ax plus b minus the expectation of ax plus b squared. We can use the linearity of the expectation value to rewrite this like this. As you see, the constant b disappears. We remain with, in the parentheses, ax minus a times the expectation of x squared. We can factor out the constant a and we elevate it to the power 2. Then we use again the linearity of the expectation value to set this constant outside the expectation. And we remain with the definition of variance here. So we have the variance of ax plus b equals a squared times the variance of x. As a nice exercise, you can try to prove that the variance of a constant random variable is always 0. Before considering quantitative examples, it is interesting to give a qualitative interpretation of the following densities. Let's start with the blue one. As you can see, it is symmetric and peaked in 0. As a consequence, its expectation value is 0. However, due to the large spread, its variance is the largest among the three depicted. Now let's consider the red one. Again, it is symmetric and peaked at 0. So the expectation value is again 0, but it is more probable than for the blue density. This is because the red one is less spread around 0, and so it has a smaller variance. Finally, let's consider the green density. As you can see, it is again symmetric, but this time it is peaked at 5. As a consequence, the expectation value of the random variable that it represents will be 5, and with a quite high probability, because as you can see, the spread and so the variance is the smallest one. Now we have all the information to review the most common probability densities, which we're going to do in the next section. In this section, we discuss the most common density distributions. We start with the discrete and then we analyze the continuous ones. The easiest discrete distribution is called uniform. A discrete random variable x has a uniform distribution if its probability mass function is represented by this formula here. The reason why it is called uniform is because it puts equal mass to each of the outcomes. Let's compute the expectation value and the variance of a random variable x that satisfies a discrete uniform distribution. For that, we must use these identities here. Let's start with the expectation value. By definition, we have that E of x is defined as the sum over all the values that the random variable takes times the probability mass function. Since this one is represented by 1 over n, which is independent of x, we can take it out of the sum. Then we compute the sum by using this identity. We recognize that we can cancel n at the numerator and the denominator, and we remain with n plus 1 divided by 2, which is the expectation value of the uniform distribution. Now let's discuss the variance. We use this formula here. Since we have just computed the expectation value, its square is simply given by n plus 1 squared divided by 4. So what remains to do is to compute the expectation value of x squared. This is given by the sum for x that goes from 1 to n of x squared times the probability mass function. As before, we can take off the sum 1 over n, and then we use the second identity to compute this sum. We recognize that we can erase n at the numerator and denominator, and we remain with this quantity here. Putting all together, we have that the variance is given by this quantity minus this quantity. If we simplify, we obtain n squared minus 1 divided by 12, which is the variance of a discrete random variable with a uniform distribution. Let's now discuss the Bernoulli distribution. Jacob Bernoulli is one of the founding fathers of probability, and he belongs to the most important family of mathematicians and physicists of all time. The idea behind this distribution is that of a Bernoulli trial, which is an experiment with two and only two possible outcomes. A discrete random variable x has a p-Bernoulli distribution if x takes values 1 and 0 with probabilities p and 1 minus p respectively. The value x equals 1 means success in a Bernoulli trial, and p is called success probability. On the contrary, x equals 0 means failure in the Bernoulli trial. Let's see what are the expectation value and the variance of a p-Bernoulli random variable. The expectation value is p, and the variance is p times 1 minus p. Let's verify the formula for the expectation value, using the fact that by definition, to compute this, we have to sum the values taken by x multiplied by their distribution. However, a Bernoulli random variable takes only the values 1 and 0 with probabilities p and 1 minus p. Hence, the expectation value is 1 times p plus 0 times 1 minus p. We can erase this term and we remain with p. We repeated the same reasoning for the computation of variance, knowing that the expectation of x is p. Hence, the variance is the expectation of x minus the expectation of x all that square. We write the first term in which x takes the value 1. This term here is always p, and so we have 1 minus p squared times p, that is the probability associated to 1, plus the second value that the Bernoulli random variable can take, that is 0, minus p squared multiplied by 1 minus p. this simplifies to this expression. We recognize that we can factor out p and 1 minus p, so we put it here, and we remain with 1 minus p plus p. We erase minus p and plus p, and we remain just with p times 1 minus p. There are many experiments that can be modeled as a sequence of Bernoulli trials, for example the repeating tossing of coin, gambling games, for example roulette, election polls, and several others. The binomial distribution is closely related to the Bernoulli distribution. Consider a sequence of n identical and independent Bernoulli trials, each of which represented by the random variable xj defined as before. If we take the sum of these n independent Bernoulli random variables, we obtain a novel one, and it is possible to prove that x has the following probability mass function. We recognize the binomial coefficient n over the value taken by x, multiplied by the probability elevated to x, times 1 minus p elevated to the power n minus x, where x goes from 1 to n. This is called an NP binomial distribution. The reason behind the name is of course the fact that there appear the binomial coefficient. The expectation and the variance of the binomial distribution are given by these formulas here. So the expectation is n times p, and the variance is n times p times 1 minus p. Below you can find the proof for the formula of the expectation value, and of course I strongly encourage you to read it. However, the computations are quite technical, and so I prefer to show the binomial distribution in action with a concrete example. We want to compute the probability of obtaining at least 1/6 in 4 rolls of a fair die. If you think about it for a second, you understand that this experiment can be modeled as a sequence of 4 Bernoulli trials with success probability given by 1/6, with success probability given by 1 over 6. Why that? Well, because each number from 1 to 6 has the same probability of appearing, and so we have to take 1 divided by 6. The key to solve the exercise is to define the following random variable. X is the total number of 6 in 4 rows. This definition is of course compatible with the idea of modeling each die roll as a Bernoulli trial, in the sense that we consider success the fact of obtaining 6 and failure the fact of obtaining all the other numbers. So, to resume, we consider x as a discrete random variable with binomial distribution for 1 divided by 6. 4 is of course n, the number of trials, and 1 divided by 6 is the probability. Now, regarding the probability, a moment of thought shows that the probability of obtaining at least 1/6 is the probability that x takes values straightly greater than 0. However, x, of course, takes always values that are non-negative. So the situation is the following. Either x equals 0, which means no 6, or x greater than 0, which means at least 1/6. It is clear that these two situations are mutually exclusive. For this reason, we can write probability of x greater than 0 plus probability of x equals 0 must be equal to 1. This simple analysis shows that the probability of having at least 1/6 after 4 rolls of a fair die is 1 minus the probability of having no 6 after 4 rolls of a fair die. By recalling the NP binomial distribution with these choices, that is x equals 0, n equals 4, and p equals 1 divided by 6, we can write this binomial distribution here. Then we have to write 1 minus this value, and if you do the computation, you obtain 1 minus 5 divided by 6 to the power 4, which is roughly 0.52. Now let's consider a slightly different game. This time we roll a pair of dice 24 times and we ask for the probability of getting at least one double 6. It turns out that the difference between the previous game and this novel one is what started the mathematical analysis of probability. In fact, if you recall the beginning of this course, I told you that the gambler Chevalier de Marais asked his friend, the mathematician Blaise Pascal, to help him understand why he was losing money betting on the fact that the probability of obtaining at least 1 6 in 4 rolls of a die was the same as the probability of getting at least a couple of 6, this time in 4 times 6, that is 24, rolls of 2 dice. This explains why in this new game we consider 24 rolls. For one die, we consider the probability of getting at least 1 6 in 4 rolls, but when we have 2 dice and we want to consider a couple of 6 appearing, then, since the other die can take values from 1 to 6, Chevalier de Marais was pretty confident to obtain the same probability as before by allowing 6 times 4, that is, 24 rolls. We're going to see now that these probabilities are actually not quite the same, and this explains why Chevalier de Marais was losing money. The core of the explanation is the fact that the 2 dice take values independently of each other. Hence, the probability of getting at least a couple of 6 is the product of the probability of getting at least 1 6, that is, 1 divided by 36. So this time we have to define this novel random variable, that is y is the number of double 6 in 24 rows, and the distribution of y will be a binomial one with n equals 24 and p equals 1 divided by 36. If we repeat the same computation as before with these novel data, we find a probability of around 0.49. As you see, the probability has decreased. And the reason is that the novel number of rolls is not large enough to cope with this quite brutal decrease of probability. I prefer to conclude the lesson here and pick up with common probability distributions in the next lesson. This will give you the time to absorb the concepts that we have covered in this lesson without feeling overwhelmed by too much information at once.